Welcome to this masterclass explainer. Today we're taking the Hall effect. Yeah, that classic phenomenon you probably tackled back in your undergrad physics courses, and we're cranking it all the way up to a complex master's level topological framework. We have some serious solid-state physics ground to cover today, so grab your notes and let's dive right in. Here's the syllabus for our journey today. We're going to cover origins and high field limits, semi-classical electron dynamics, Fermi surface topology, the conductivity tensor, Group 1b metal orbits, and finally, magnetic metals and anomalies. Section 1. Origins and high field limits. Okay, let's establish our baseline before we get into the heavy quantum topology. Picture a standard rectangular sample. You've got an electron flow, you apply a perpendicular magnetic field, and boom, the Lorentz force kicks in. The cross product of velocity and the magnetic field deflects these free electrons toward one face of the sample. Now, initially, this creates a transient transverse electric current. But, electrons are mutually repulsive, right? They can't just pile up there indefinitely. So in the steady state, a transverse concentration gradient sets up. This produces the Hall field that exactly opposes any further deflection. It's just a beautiful classical equilibrium. But here's the thing. If we want to study the intrinsic topological properties of a metal, we can't just hang out in the low field limit where everything is dominated by random electron scattering and collisions with phonons. We have to force the system into what we call the high field limit. Mathematically, this is the regime where the cyclotron frequency times the relaxation time, omega sub c times tau, is much, much greater than 1. In this state, an electron completes multiple cyclotron orbits before a single collision even happens. To pull this off experimentally, you need ultra-pure samples at very low cryogenic temperatures. When you do that, the Hall effect becomes this incredible direct probe of the Fermi surface geometry itself. Section 2. Semi-classical electron dynamics. So, with our strict high-field condition locked in, we need to define how these electrons are actually moving through momentum space, or k-space. Looking at the semi-classical formulation, the motion is governed by a fundamental geometric relation. Force equals the time derivative of crystal momentum, so F equals dp/dt. Now, because the magnetic force is always perpendicular to velocity, the electron's energy remains strictly constant. It traces a cyclotron orbit precisely on the constant energy Fermi surface. And the frequency of that orbit, the cyclotron frequency, omega sub c, is intrinsically tied to the applied field H and, crucially, the effective cyclotron mass, M star. Remember, this isn't just a free electron in a vacuum. That effective mass perfectly accounts for the periodic lattice potential the electron experiences on that specific orbital plane. Section 3. Fermi surface topology. Let's be real for a second. Perfectly spherical Fermi surfaces are pretty much a myth once you get into actual solid-state physics. The reality is geometrically complex. When a real multiply-connected Fermi surface makes contact with the Brillouin zone boundaries, it supports highly intricate electron trajectories across the reciprocal lattice. So as the magnetic field is applied, the electron is guided along these sweeping, continuous open contours, rather than just simple closed loops. We can meticulously categorize these topological trajectories into 4 main types. First, we have closed orbits, which act as either electron-like or hole-like, depending on whether they enclose filled or empty states. Second, extended closed orbits. But third, and definitely pay attention to this one, we have periodic open orbits. These act as critical topological boundaries moving from zone to zone in the extended zone scheme, literally separating distinct belts of electron orbits from belts of hole orbits. Finally, we have aperiodic open orbits. Section 4. The conductivity tensor. To handle all this geometric complexity mathematically, simple scalar equations absolutely won't cut it. We need robust tensor expansions, specifically the framework developed by Lifshitz, Asbel, and Keganov. By expanding each element of the conductivity tensor, sigma ij, as a power series in inverse H, we can solve the Boltzmann equation in the high field limit and prove something mathematically remarkable. Notice that as H approaches infinity, meaning H to the negative 1 approaches 0, the closed orbit contributions to the diagonal elements scale as H to the negative 2. They effectively vanish. This means the resulting tensor is governed almost entirely by the off-diagonal open orbit geometry. It beautifully reduces a highly complex multi-band problem down to a system of quasi-free electrons moving along specific inclined planes. Section 5. Group 1b metal orbits. Theoretical tensors are great and all, but let's map this mathematical framework directly onto some real-world metals. Group 1b, which is copper, silver, and gold. When we map their k-space cross-sections, we observe some severe topological deformations. Because their Fermi surface actually makes physical contact with the boundary faces of the Brillouin zone, it creates what we call necks. These necks fundamentally alter the conductivity pathways, completely ruining any assumption of a simple free electron sphere. Specifically, the geometry of these necks forces electrons into some wild orbital bands. When the external magnetic field aligns precisely with the 001 and 110 crystallographic axes, we get these fascinatingly named rosette and dog's bone orbits. And here's the kicker: these are whole orbits. Because they act as positive charge carriers in the high field limit, the emergence of these specific topological orbits dictates a net positive shift of the overall Hall coefficient for these metals. That is a perfect, tangible example of topology directly driving a macroscopic, measurable quantity. Section 6. Magnetic metals and anomalies. Up to this point, we've dealt strictly with non-magnetic lattices. But now we have to introduce the profound complications caused by localized magnetic moments. This brings us to the anomalous Hall effect. Unlike everything we've discussed so far, this is a spontaneous transverse electric field. In these materials, the external magnetic field isn't providing the Lorentz force pushing the electrons around. Rather, it merely aligns the magnetic domains to reveal a spontaneous, intrinsic asymmetry. This asymmetry is rooted deeply in quantum mechanical phenomena. Think the Kondo effect and spin-orbit interactions within the lattice. The step-by-step microscopic mechanism here is absolutely wild. When a conduction electron approaches a magnetic irregularity, like a localized spin domain, it experiences an asymmetric scattering potential. It is energetically forced to scatter preferentially to one side of the ion. Imagine a massive stream of electrons, and because of their spin interactions, they're all selectively getting bumped to the left. In the steady state, this preferential deflection builds up a massive transverse voltage that is completely independent of the classical Lorentz force. It's literally a pure scattering anomaly. So we have rigorously mapped the static lattice topology of solid-state physics today, moving all the way from the basic Lorentz force to quantum spin scattering. But I want to leave you with this provocative thought to guide your future research. We relied heavily on a highly ordered periodic crystal lattice for these models. What do you think happens to the Lifshitz-Asbel-Kaganov tensor, or these asymmetric scattering potentials, when we apply them to the chaotic, disordered structure of liquid metals, or even crazier, the zero-resistance environment of superconductors? Keep questioning, keep calculating, and I'll see you in the next explainer.